Hello there, scientific brilliant people. How are you today? So today I'm going to discuss about a problem from oscillation, and we have to prove whether this oscillation is a case of simple harmonic motion or not. So here we have a U-shaped vessel in which we have liquid of density rho L, and we know that liquids are incompressible, so the volume of the liquid is going to remain constant. Now liquid attains its own level. So that means the height of the liquid in this arm and this arm will be same, and that is h. Now what am I going to do is I'm going to put my finger inside and I'm going to exert force. That force divided by this area will become pressure. So I am exerting pressure in the downward direction, but the fluid can't be compressed. So the fluid will travel down by some distance, say y centimeters in the downward direction. Now the same amount of fluid should go up in the upward direction, as the volume of the fluid can't be changed. So if I put my hand like this, from here the liquid goes by y centimeters down, and from the other side, from this common level, the liquid will go by y centimeters in the upward direction. Now people, we have 2 points, right? We are talking about this point and we are talking about this point. Now since in this particular position, when my finger is still inside, the liquid is stationary, no movement, because the pressure exerted by me at this point and the pressure exerted by this liquid column at this point is same. So the pressure at this point and the pressure at this point is same. So when the pressures are same, no pressure difference, liquid will not be in motion. And the pressure over here is due to my finger, and the same pressure is due to the weight of this extra column of liquid that has gone up. So now the total length of the liquid column is y and y, so that is 2y. So the entire length that we see over here is 2y, correct? Because I'm talking about this point, so from this point y centimeter has gone up. So from this point already the liquid was at y centimeter, now y centimeter extra. So that means at this point and this point the pressures are same. If I remove my hand, this pressure becomes more, which is due to the weight of this column divided by the area. This pressure will be more, so the liquid will move from high pressure to low pressure, and you will see this situation. Again, if you look at these 2 points, at this point and at this point, this liquid column, due to its weight, it is going to apply pressure over here, which is more than the pressure over here. So again, liquid will move from high pressure to low pressure. So in this way, the liquid will keep on oscillating. But whether the liquid is performing simple harmonic motion or not, that we can't say right now. Okay, so this is simply an oscillation. We have to prove whether this is in simple harmonic motion or not. If this liquid obeys this condition, where F is the restoring force and Y is the displacement, so we know that any restoring force is opposite to the displacement. This is the condition of SHM. So if we are able to find out what is the restoring force over here, and if that restoring force is opposite to the first power of the displacement, then and only then it would be a case of simple harmonic motion, people, right? So I am pushing this liquid down by y centimeters. So at this point the liquid goes by y centimeters up, and the total liquid column is having height 2y. Now the weight of this liquid column divided by this area, which is A, the area is the area of the surface, this area would be the pressure. So let me find out first of all the weight of this liquid column, because this weight is responsible for the pressure and that weight is responsible for the oscillation. So weight of this liquid column is equal to m into g, where m is the mass of this liquid column, that is equal to density of the liquid times the volume of this column. Volume if this column is A, that is the area, multiplied by the height, that is 2y, times g. So this is mass and this is the acceleration due to gravity, correct? So this is the weight of this part of the column. Now people, this weight behaves as a restoring force. Why? Because this weight will again bring this liquid back to this position and then to this position. So that means this weight is a restoring force. Now I'm going to replace this W by restoring force. Now that is equal to rho 2, I'm just rearranging, 2a rho L G times Y. As you can see, this part is constant and this weight is directly proportional to the first power of Y. So that means this is a restoring force and it is a case of SHM, because now the restoring force is proportional to the first power of the displacement. Now restoring force, which is the weight of this liquid column, if I write in vectors, because the weight is in the downward direction, people, and the displacement was in the upward direction of this column. So that is equal to minus 2a rho L G times Y vector, which is in the upward direction, and FR vector is in the downward direction. So that means this behaves as K. If I compare this equation 1 and this equation 2, this equation, in this equation this part becomes K. So K is equal to 2a rho L times G. So this is the first equation, people, that I am getting over here. Now let me find out the time period of the oscillations of the first value of K I am getting over here. Let me put a star over here, people. We know that any object performing SHM has time period T is equal to 2 pi under root m by K, where m is the mass that is oscillating. Many people get confused that what is m over here. The m is the mass that is oscillating. So many people consider this as the mass, which is incorrect. Here the entire liquid column is oscillating, people. So we have to take the mass of the entire liquid. Now I'm going to make an assumption that this tube is just like this, whose arms are very near. Now we have considered this as H, this part is A, and the density of the liquid is rho L. This is again A, this height is again H, like that. So now mass is equal to density times volume, and mass of what? Mass of entire liquid. So mass of the entire liquid is equal to density of the liquid times volume of the entire liquid. Now since I am considering both the arms very near, I am going to neglect this part. So this becomes a very simple two cylinders, right? So this is A times H, and the total volume would be 2AH. So this is the volume, this is the density. So the total mass of the liquid over here is now rho L 2AH, which I'm going to substitute it over here. So now T is equal to 2 pi, then mass of the entire liquid, that is 2 rho L H A, divided by K, that is the force constant, which is here 2a rho L G. Now as you can see, people, over here 2 gets cancelled, rho L gets cancelled, A gets cancelled. So finally we get T is equal to 2 pi under root H by G, which is the equation of time period of SHM. So people, first of all, learn about which is the restoring force. Find out that restoring force, like over here, the weight of this liquid column was able to bring the entire liquid to its own place. So the weight of this liquid was the restoring force. Now you have to find out whether that force is proportional to the first power of displacement and opposite to the direction of displacement. If it is so, it is an SHM. Otherwise, it would be simply an oscillating liquid, not simple harmonic motion. Now, after doing that, find out, compare this equation with this. This is the equation of SHM, restoring force. Now, from here, find out the value of K, substitute the value of K over here, and remember, M is the mass of the liquid which is oscillating. So here the entire mass of the liquid is to be considered, which is to be considered like this. So hopefully, people, you have enjoyed the explanation. If you have any doubts, please do comment in the comment section. I am going to again come back with another example of the oscillation, which is possibly again a simple harmonic in nature. Thank you for watching the video.